Welcome to ES 310 Lesson 15. Today we're going to be extending the work we did in Lesson 14 on conservation of momentum to look at impact problems, so problems that have impulses that happen over a very short period of time and involve the coefficient of restitution, which is a measure of the loss of energy in the impact. This will allow us to find or to predict the final velocities of two objects, knowing only the initial velocities of those two objects and the coefficient of restitution. More information on this topic can be found in Hibbeler's Dynamics text, Chapter 15, Section 4. So impact is, as I said, an impulse that happens very quickly. So let's take a look here at this video and see the impact of a golf ball. So as it comes in, it is undeformed. As it hits, it will deform, and then it will be restored to its original shape and go back in the opposite direction. So in that impact, there are 5 stages. So immediately prior to impact, we have some momentum of the ball plus the golf club, which in this case wasn't moving, but could have been moving. Then during impact, we have a momentum, an impulse, and another momentum, right? So this is the momentum of the ball A. There's a similar equation of ball for the golf club B. Then they move together for a short period of time. In this case, it was when the ball actually physically stopped, since the golf club wasn't moving in this video. And then there's restitution, which is another impulse, and the momentum before and after for each ball, the ball and the club. And then immediately after impact, we once again have this sum of momentums. There are 2 types of impacts that we're going to look at today. There's central impact, where the direction of motion of the 2 particles that collide are along the line connecting those their mass centers. So if you draw the line connecting their mass centers, call that the x-axis, then the motion is along the x-axis. The oblique impact is where the direction of motion is not along the line connecting the centers. So connect the centers, call that the x-axis. The motion of the particles will have a component in the x-axis and a component along some other axis. And we'll look at both of these today, and the procedure we're going to be using to solve them will be different. So coefficient of restitution is the new topic for today. It's a mathematical equation. It's a coefficient, so it has no units. And what it does is it captures some information about how much energy is lost. It's the ratio of the relative velocity of the particles separating after they hit to the relative velocity of those particles approaching each other before they hit. So mathematically, the velocities after are on the top, the velocities before are on the bottom. All right, so 2's are on the top, 1's are on the bottom, and they're in the reverse order. So if we do VB2 minus VA2, then it's going to be VA1 minus VB2. There's 2 extremes here, right? E can be equal to 1, in which case you have purely elastic impact. No energy is lost. So this is the ideal case, but it's also not realistic. In the real world, you will never see this. You could also have E equal to 0, which is plastic impact, and that's where the 2 particles stick together. So remember, we had an example where we had a car hit a bus, and then they get stuck together and they keep moving. That's the case where E is equal to 0. So the final velocity of the 2 are the same, so the numerator of E is equal to 0. So all of E is equal to 0. There are 2 different procedures we're going to use today, one for central impact and the other for oblique impact. So for central impact, we're going to apply the conservation of momentum, we're going to apply the coefficient of restitution, and we'll have 2 equations and 2 unknowns. Note, we're going to do this for each of the directions. So we could do this for the x direction and the y direction. In oblique impact, we're going to define the line of impact, the x-axis, as that line connecting the center of masses. And then we'll look at information along the x-axis and along the y-axis. So along the x-axis, we've got the conservation of momentum, coefficient of restitution, and we can solve for ax2, or the velocity of A in the x direction after impact and the velocity of B in the x direction after impact. In the y direction, there is no impulse, right? Because all of the impulse is happening along the line of impact, which is the line connecting the two centers. And so there isn't going to be a change in velocity. So let's take a quick example of this. This is a central impact. Ball A is going to roll down and hit ball B. That's going to cause ball B to move and hit ball C. And we need to figure out what is the speeds of all three particles after all the impacts. And the balls are heading along the direction of motion. So this is central impact. They all have the same weight, which is 0.5 pounds. And there's a coefficient of restitution of 0.85 for each of them. One comment to make about coefficient of restitution is that it depends on both particles and the situation that they're in. And so you can't have a golf ball that has a coefficient of restitution, even though you hear about golf balls that have a specific coefficient of restitution. Coefficient of restitution will also depend on whether that golf ball is hitting a brick wall or being hit by a titanium club. So you have to keep that in mind. It depends on both particles. Alright, so we've got ball A, B, and C. Let's first look at ball A. Ball A starts at rest, so this part, from where it starts here until it moves down and hits ball B, we've got a conservation of energy problem, right? Because we need to figure out how fast is it going when it hits ball B. And so by conservation of energy right now, sitting up here, it's got potential energy, which is mgh. And when it gets down to the bottom, it will have kinetic energy, which is 1/2 mv squared. So the m's will cancel. We know g and h, so we can find v. This is VA, the velocity of the ball A, before impact, so 1. And it will be, if we plug in those numbers, 13.9 feet per second. Alright, so we now know the velocity of A before impact. We've got the impact 1 is going to be AB. So we've got mVA1 plus mVB1. So that's the conservation of momentum. So momentum before the impact is equal to mVA2 plus mVB2. Alright, so the conservation of momentum is one equation we have. They are all the same mass, so those cancel. We also have coefficient of restitution, because ball A and B have a coefficient of restitution of 0.85. So coefficient of restitution is equal to the velocities after over the velocities before. So we'll do VB2 minus VA2 divided by, and they switch order, so VA1 minus VB1. Alright, VB1 is 0, right, because the ball B is not moving initially. And so this is equal to 0.85. And VA1 we found was 13.9, so this is 13.9, this is 13.9. And so we have two equations and two unknowns. And so we can solve two equations and two unknowns will give us VB2 of 12.85 in that direction and VA2 of 1.05 in that direction. This might be a good point to review how to use your calculator to solve simultaneous equations, because there will be a lot of simultaneous equations in this section of the class. Alright, so then we also have the impact of ball B hitting ball C. So similar two equations, we've got mass VB before, which is going to be the 2, right, because it starts moving here, it doesn't lose any speed before it hits C, alright, plus mass of ball C2 is equal to mass of ball B3 C3 after impact, mass of ball C3. And we have coefficient of restitution, so the afters are on top. We'll do C first, then B, and B first, and then C for the befores. Alright, VC is 0, VB was what we found before, 12.82, whoops, 4.85. VC2 is 0, this should be a 2. And this is 12.85, and the m's all cancel because they're all the same. So we have, once again, two equations, two unknowns. We can solve those, and we get VB3 equal to 9.965 this direction, and VC3 equal to 11.9 that direction. Alright, so we have the final velocities. VA is moving like this at the final velocity, B is there, and C is here after all of the impacts have hit. So now let's take a look at a problem where we've got 2D impact. Alright, so we're throwing a ball against a brick wall. Brick walls or other unmoving objects are sort of special cases because they don't move before or after. Right, so the coefficient of restitution really does give how much does the velocity of the ball change. Alright, so this one, the girl throws the ball, it bounces on the wall, and it comes back out, and we're trying to find S. So there's three parts to this problem, right? We've got projectile motion as the ball goes from A to B. We've got coefficient of restitution and conservation of momentum at B for the impact. So the impact is happening up here. And then we have projectile motion again from B to C to find S. So let's take a look at this in the three parts then. So part 1 is going to be our projectile motion from A to B. Alright, so if this is 2D projectile motion, we know that the x direction changes by 3, alright, because we're moving 3 to the wall. The x direction of the initial velocity is 10 cosine 30. The y direction of the initial velocity is 10 sine of 30, which is equal to 5. For the x side of things, we have the change in position is equal to the velocity times the time, so we can find the time to be 0.346 by plugging these two numbers in here. Alright, so now knowing the time and the initial velocity over here, we can find the final velocity. So the velocity of the ball in the y direction at B. So all of these velocities are the velocities of the ball. So this is the velocity at B in the y direction is equal to, so that's the final velocity, is equal to the initial velocity minus g times t. Alright, so if we plug in numbers, we get this final velocity is equal to 1.6. At the same time, we can also find the change in position, right, from here up, delta y. And delta y is equal to the initial velocity times t minus 1/2 of g times t squared. We know t, g, and initial velocity, so delta y is going to equal 1.14. So our velocity written as a vector then, the velocity of the ball at B is going to equal the x part, which is this 10 cosine 30 becomes 8.67 I hat, plus the y part, which is 1.6 j hat. Alright, so that is our vector notation for the velocity at B. Now let's take a look at that impact. Alright, so we've got the impact. which is part 2 at B. The line connecting the ball and the wall would be in the x direction. So there's going to be impact in the x direction. The velocity is going to change. It's going to reverse its direction, and it's going to change its magnitude. But in the y direction, there is no impact, right? Because the ball does not exist in the y direction. So in the y direction, we have the velocity of the ball at B in the y direction before impact is equal to the velocity of the ball at B in the y direction after impact. And that is equal to 1.6. So we've taken care of the y direction. Now let's look at the x direction. So in the x direction, let's use our coefficient of restitution equation. So we have E is equal to the velocity of the ball at B in the x direction after impact minus the velocity of the wall after impact, divided by the velocity of the wall before impact minus the velocity of the ball at B in the x direction before impact. So the wall's not moving, so this is going to be 0 and this is going to be 0. E is equal to 0.5, so this then allows us to say that the velocity of the ball at B in the x direction after impact is 0.5 times the velocity of the ball at B in the x direction before impact, which we know is 8.67. So the velocity of the ball after impact in the x direction is negative. Oops, we lost our negative sign. Negative, right, because we're multiplying this negative number over, is going to be negative 4.33. Which makes sense, right? If we look at this, we're coming in positive, we're going to go out negative, we're coming in with a bigger velocity than we're going out with because we lost energy. So both of those things make sense. So we now have our velocity, we can write it as a vector. The velocity of the ball at B after impact is equal to, this would be before impact over here, is equal to negative 4.33 I hat plus 1.6 j hat. And now we have projectile motion again, right, from B to C. So we'll see if I can squish it in down here at the bottom. From B to C, what do we know? We're trying to find delta x. We know the VBX is equal to negative 4.33. We know VBY is equal to 1.6. We know delta y is equal to the 1.4 that we found, 1.14 that we found before, plus 1.5. And it's going downwards, because if we start up here, we end up down there, we're going down. So that's negative 1.14 minus 1.5. And then our two equations, we've got delta y is equal to VBYT plus 1/2 g, minus 1/2 g t squared. We know delta y, we know the initial velocity in the y, so we can find t. So this gives us t is equal to 0.915. And then knowing t, we can go to the x side and say that delta x is equal to VBX times t, which gives us negative 3.95 meters. All right, so it's moved backwards 3.95 meters. And that then is our final answer. So part 1 and 2 should be familiar to you from the first chapter we did, projectile motion, nothing's changed there. The impact at B is what's changed, and because we have this stationary wall, the only equation we are going to use is the coefficient of restitution, because conservation of momentum doesn't give us any useful information. All right, for our last example, let's look at oblique impact. So oblique impact means we've got velocity 8 here and 10 here that is not along the line that connects the centers, which is this line right here. The line of impact connects the centers, not aligned with our velocities. Alright, so how do we deal with this? Well, we look at the y direction and the x direction. So first of all, we need to break these velocities into the x components and the y components along not this x or that y, right? But we define the line of impact as our new x and the line perpendicular to impact as our new y. And that's the x and y we're going to use for this problem. So we can write then the velocity of A as a vector is going to equal the 10 times the component that's along the x and the component that's along the y. So if we draw those, we've got this one and that one. Alright, this one, if we're looking at this triangle, the hypotenuse is going to be 5, right? Just to keep in mind, if that's 5, then what angle which is which? So if this then is 5, this angle here is the same as that angle, right? Because they're this is parallel to this is parallel to that. Right, this angle here. All right. So this angle, this part would be the 3, right, between the 5 and the 5 angle 3, and this part would be the 4. Do a similar thing over here. We've got this part and that part, right? If this is 5, this angle here is now over here. So this is the 3 leg and this is the 4 leg. Alright, so looking at those triangles, then the x part is going to be the 3 part. So it's going to be -3 over 5. And the negative is because this would be going down and positive is going up. So that's I hat. Plus the 4 part is the j hat, and that's in the positive direction. Do the same thing for B. We have 8, and we've got the 3 part again in the x direction, and it is positive this time, so 3/5 I hat plus 4/5 j hat. No, minus 4/5 j hat. That's in the negative direction. Alright, so that's our vector notation for our speeds. Now let's look in the y direction. The y direction is the easy direction because no impact occurs in the y direction. If no impact occurs, then there's no change in velocity, so VB2 y, well, let's start with A. So VA2y is equal to 10 times 4/5. Right? It doesn't change. VB2y is equal to 8 times 4/5 negative. Also doesn't change. This is negative 6.4. Alright, now we look at the x direction. That's where we have work to do. So in the x direction there is impact. We have 2 equations. We have the conservation of momentum, and we have the coefficient of restitution equations. So conservation of momentum says the mass A times the velocity of A before impact in the x direction plus mass B, velocity of B before impact in the x direction, is equal to mass A, velocity of A after impact in the x direction, plus mass B, velocity of B after impact in the x direction. So plugging numbers in, mass of A is 15, speed of A, 1 is 10 times negative 3/5 plus 10 is the mass of B times 8 times 3/5 is equal to 15 times the unknown velocity of A in the x direction 2 plus 10 times the unknown velocity of B in the x direction 2. So that's our first equation. Our second equation is coefficient of restitution, so E, which is 0.8 in our case. Final velocities are on the top, so we have V, B, x2 minus VA x2 divided by initial velocities on the bottom, switched order, VA x1 minus VB x1. So these unknowns are on the top, and in the bottom, x1, that's negative 10 times 3/5 minus VB, which is 8 times 3/5. And so we have two equations, two unknowns. Plug them into your simultaneous equation solver, and we get AX2 1.776, ABX2 is negative 6.864. And so we can write our vector notation then. VA2 is equal to 1.776 I hat plus 8 J hat. It's coming from up here. And VB2 is equal to negative 6.864 I hat plus, minus 6.4 J hat. And that then is our final answer.